You have found the second part of a video covering the aerodynamic design of the UWS-4 Ultralight aircraft. This is a multi-part series. We're actually in part 6 right now, second part of part 6. And in this part 6 video, we're looking at the tail geometry of our ultralight airplane. We're trying to figure out where it's going to be on the airplane, what the size of that tail is going to be, and the shape of the tail. Now in the first half of this video, part 6A, we talked about why in the world we might even want to have a tail. It's not because most other airplanes have one. There's actually a purpose for it, so we talked about what that is. Then we talked about the method we're going to use for figuring out the surface area for the tail. In this case, we're using the tail volume method. And so we talked about how we're going to use that. We also talked about some of the desires that I had for this airplane, some of the goals that are going to help drive what we're going to choose for this tail. And one of those was to help reduce drag on this airplane because I want to be able to fly to some local airports that are fairly far away. So I want to get some good range out of this airplane. And so one of the ways of doing that is reduce the drag. So I want to keep the tail out of the slipstream of the prop on the airplane. So we talked about some of the considerations we're going to give to try to do that. And so I decided I wanted to look at an inverted V-tail. So that is where we are going to begin in this part of the video. We're going to talk about some of the drawbacks and some of the advantages of that inverted V-tail. Now, if you're new to this series, we're using Dan Raymer's book, Simplified Aircraft Design for Homebuilders. And we're using it as a guide to help us design this airplane. It's a really nice, fairly small book, and as the name implies, it is a pretty simple method for designing an airplane. And so far, we've really liked using it. Well, let's get started. Now, there are some advantages and disadvantages of a V-tail over a horizontal and vertical tail. Let's talk about some of the disadvantages. There could be more than I'm going to specify, but at least some of the bigger ones, let's talk about them. Connecting up a V-tail to your controls is slightly more complex. Now, on a typical vertical tail, you can hook up that vertical tail directly to your rudders. And the horizontal tail can be hooked up directly to your stick. But with an inverted V-tail, you got both rudder and pitch on your control stick. Both of those are combined to move the two tail surfaces on your V-tail. So you have to have a slightly more complex mechanism to mix those two control inputs together to control your two flying surfaces on the V-tail. Now, one of the problems with having a slightly more complex control mechanism is you're increasing the likelihood of a failure. Now, if you have a failure in your pitch control, it's very likely that you're going to have a severe problem, and if you don't have a parachute, it's a good possibility you're going to impact the ground at a high rate of speed. Now, fortunately, we're going to put a parachute on this airplane, so it's not quite as critical, at least as long as we have some altitude to deploy the parachute. But I am slightly increasing the risk on this airplane by going with the V-tail. Now, Dan also mentions that some V-tails seem to have a little bit of problem in spin recovery. Now, he didn't go into specifics on that, and of course, that's because this is a simplified book. But what I would like to do is, after I come up with my initial design for this airplane, I'd like to try to do some computational fluid dynamics simulations to see if I can figure out if there might be some spin recovery problems with this airplane. So hopefully we can address if this is an issue or not. If it is an issue, we'll either change the design of the V-tail or just give up on it and go back to a simplified horizontal and vertical tail. Now, what are the advantages of the V-tail? Now, in my case, when I'm trying to keep that tail out of the slipstream, having an inverted V-tail matches up perfectly with having booms that go out beside each side of the prop and hook up to the bottom of the inverted V-tail. And we'll look at that here in a moment so you can see a picture of what I'm talking about. So that actually is kind of an advantage of having the inverted V-tail. And it makes it a little bit easier, of course, to keep the tail out of the prop with this inverted tail. We'll take a look at that again, so that helps reduce your drag. Another nice thing that's kind of cool about the inverted V-tail. Now, the not inverted or upright V-tail actually has a problem, and that's that it tries to roll the airplane in the wrong direction when you apply rudder. Here I'm showing a V-tail where the control surface here is deflected down, here it's deflected up. And that's when we're putting in a right rudder input on our rudder pedal. So we're not putting any pitch input in. So that pitch is neutral. So here I've drawn the forces. So here's the force perpendicular to our control surface. So here, this surface is causing this portion of the VTail to push up and to the left. And over on this side, it's down, but still to the left. So if you look at this green arrow, this is a component, the horizontal component of this force. So we got a force to the left, force to the left. So forces to the left on the tail causes the nose to go right. So this will be a yaw to the right. But we also have an upward force on this side and a downward force on this side. Now, as far as pitch goes, this upward force and downward force cancel each other out. So there's no up or down total force. But you'll notice that this force is to the right of the center line and this one's to the left of the center line. So this actually causes a roll to the left. This one's pushing up, causing a moment to the left, and this one's pushing down on this side, also causing a moment to the left. So it's trying to roll us like this. Well, that's the exact opposite of what we want. Generally, when we're yawing to the right, we also want to roll to the right. So VTail puts in a roll in the opposite direction that you want. And that's not really a very good thing. But an inverted VTail actually tries to roll it in the correct direction when you apply rudder. This is an inverted VTail, as you can see, and again we're putting in right rudder input. So in this case, this control surface is deflecting up, which is pushing down to the left. This one is deflected down, pushing up and to the left. So again, we have left forces here on the tail, which is going to cause us to yaw to the right, same as with the previous slide. But now let's look at roll. Well, once again, we have a down force and an up force that are going to cancel each other out for pitch. But it's also going to cause us to roll. So this is going to go down this direction, causes us to roll to the right, and this one also is going to cause us to roll to the right. So we're yawing to the right and rolling to the right. So this is a more desirable tail configuration than the upright V. So that's kind of a nice thing about using the inverted V-tail. Another thing is that the V-tail has a little bit less interference drag than the horizontal vertical tail, usually. Of course, you can screw it up, but typically you're going to have less interference drag. We've talked about interference drag in some previous videos. But basically, that's drag that you're going to have on the aft portion of a joint of two surfaces. It's a little more complicated than that, but essentially that's the location where you'd have interference drag. So for example, the joint between the wing and the fuselage, on the aft part of the wing at the fuselage, you'll generally have interference drag if you don't have good fairing there. So you can have the same thing on the tail. For example, in a place where a horizontal and vertical tail meet on the aft portion of that little junction, you'll frequently have interference drag if you can't find a good way to fair it. Now, one thing that helps a little bit here for this airplane, if I'm going to use that V-tail, is I only have to have one length number. While horizontal and vertical are the same thing. So really all I need to figure out now is what is that length for my V-tail. So now we can get into determining what that length is with a few other helpful criteria or restrictions. Now Dan talks about an issue that you can have in spin recovery when the horizontal tail is in the wake of the wing when you're in that spin or a stall. And you want to try to avoid having that horizontal tail, and in our case, our whole V-tail, out of that wake of the main wing in that stall or spin condition. And he talks about these angles, a 30-degree angle from the trailing edge of the wing and a 60-degree angle from the leading edge of the wing. And here in a moment, we'll bring up VSP Aero and talk about that specifically so you can visualize it much easier. We also have an issue of landing. We don't want to have our tail striking the ground when we're landing. So we want to have it above a 12-degree angle from where the main gear is going to touch the ground. So it has to be higher than that. So it has to be lower than this 30-degree angle or higher than the 60-degree angle from the leading edge, which really isn't feasible. So it's got to be lower than a 30-degree angle from the trailing edge of the wing, higher than a 12-degree angle from the main gear. And of course, we don't want it in the wake of the propeller. So that actually helps us in figuring out where that tail can be placed. Now here's the result, but let's actually go and look at VSP Aero and talk about visually some of these criteria and restrictions to help us figure out this tail length. Here's the wing we came up with on part 4 of our video series. And just kind of give you a better idea of the size of this, let me pop up a pilot. So here's an FAA standard weight pilot, 170 pounds. And where I think that pilot's going to sit, it's going to be about here, a little farther forward or aft, but not too much. So this kind of gives you an idea of the size of the wing. Now let's talk about placement of the prop. Let's pop up a prop here. So here's a 64-inch prop and roughly where I think it should go. Now I decided I want about 8 inches of clearance between the bottom of this prop and anything that might be below it. In this case, it could be a boom or the ground. Actually, with the boom, we could probably make that clearance a little bit less, but I don't intend to have a boom down here. So for now, that 8 inches would be down to the ground. And in particular, that would probably be when we're landing. So typically, when you're on the ground, there's going to be more clearance here. So as you can see, the center of this prop is going to be fairly close to the CG for the airplane. I would expect that CG to be probably really close to this. So that's nice. I like that. So let's assume that's about right. Okay, so I kind of like that. Now let's add in our 30 degrees from this trailing edge of the wing. That's what Dan talked about, trying to avoid the wake of the wing when you're stall or spin. So let's add that in. So I made a really thin box to represent that. So looking at it from the left, so there's the trailing edge of the wing, there's 30 degrees. So our tail has to be somewhere underneath this 30-degree line to avoid the wake of the wing. Now I also talked about a 60-degree line in front of the wing. So let's go ahead and show that. So here's that 60-degree line, and it really wouldn't be practical to put a tail up in here. So we can pretty much ignore this 60-degree line. So I'm going to go ahead and get rid of that. So our tail has to be somewhere out here in this area. Now we also talked about a 12-degree line when we're landing, that the tail has to be above that so we don't get a tail strike when we're landing. Now I kind of somewhat arbitrarily picked 12 degrees. You could pick 15 degrees if you think you're really going to come in at a steeper angle. If you think you're never going to come in at less than a 10-degree line, you could do something like that. But I picked 12 degrees just kind of as a happy medium between a shallow and steep landing angle. So let's bring in a 12-degree line. Now that 12-degree line has to intersect the bottom of the wheels. So I have to make an estimate of where that's going to be. I believe I'm going to use tail dragger landing gear. So the main wheels will probably be somewhere very close to the leading edge of the wing. So I'm going to assume the wheels are somewhere down here. So let's add that 12-degree line. So I believe the wheels will be down here, right in this area. So let's go ahead and add a 0-degree line that would be the ground. So assuming that this is where the tire is going to be, our 12-degree line and the ground should be right at the bottom of those tires. So this is the ground line. So this is 0 degrees. So the bottom of our tail has to be above this line and below this line. So our tail has to be somewhere in between these two lines. And by the way, I've already set the correct incidence for this wing. This is 5 degrees angle of incidence. So this should be the attitude of the airplane in straight and level cruise flight. Okay, now the next thing to do is to stick in a possible V-tail and see what we got. So here's a possible V-tail. The top of that V-tail is going to have to be just at or a little bit above the top of the prop. Let's take a look at the front view. Now what you're looking at here are those various angles. Let me get those out of the way so those aren't bothering you anymore. Okay, so here's the ground. Here's our 8 degrees clearance below the prop. And so here's our V-tail. Now this angle of this V-tail is what Dan mentioned should be about 35 degrees from vertical. So that's what I've chosen here. This is 35 degrees from vertical. I've also put a little bit of a span here to hook these two together. When you push forward on the stick, both the control surfaces from these two angled parts of our tail will come down. And I wanted to have enough space here that those two trailing edge corners from these control surfaces would not hit each other. So that's how I came up with this distance here. Now initially I did not have these vertical parts on here. Now I talked about having a possible tail boom. There's got to be some way to hook up this V-tail to our airplane. So one way, of course, would be to put a boom up here on the top, and that's not unfeasible. But in order to do that, I would have to extend the top of my cabin up a little bit higher in order to have that connectivity, that structure, in order to run a boom back there. Now, that certainly is a possibility. but that's going to add some weight that I really don't want to have, and some extra drag that I don't want to have, just in structure up here and looking at it from the side. So that would be structure all right up in here. So I'd really rather not have a boom coming across here, hooking up to this tail. So that means some twin booms. Let me put some in here real quick to where the initial booms were without this vertical spot here. So here were the initial booms. Let's look at it from the front real quick. So you can see that the booms are just outside of the prop. I moved them a little bit farther. And there's a reason for that, because I'm going to end up splitting this wing right about here so there's outer panels can come off and this would fit into a trailer. So let's go back to the side view. By the way, this is not really what the booms would look like. This is just a stand-in. We'll actually talk about these booms and the fuselage in a future video. So this is just a stand-in to kind of get an idea what this angle would be. And I was not happy with how steep this angle was. I wanted to have a little bit less angle. Now, one of the reasons I don't like this angle is that this is going to be a little bit like a flying surface. And because of this angle, there's going to be a little bit of a down force. This is going to try to pitch it up a little bit. Now, that's not horrible. I could actually live with that, but that means my tail is going to have to be just a little bit bigger to counteract that pitching moment a little bit. So I'd rather not do that. I'd like to actually reduce this angle a little bit. And so what I did is I added this part down here, viewed from the front, this part right here. So I took some of the surface area from up here and I added it here. That means I'm going to have just a little bit more vertical surface area than a typical inverted V-tail would have, but I think that's going to be okay. So let's go back to the side. So with that extra added in here, let's see what that boom looks like. So this would be the angle of the boom now with this little extra vertical part added in. So this still has some incline. It's still going to cause a little bit of a pitch up moment, but that's not bad. I think we can live with that. And as I said, this is only a stand-in. We'll come up with the actual boom configuration in a future video, probably the next video. So I've brought this tail as far forward as I can. If I try to bring it much more forward, I'm going to have to drop it down to keep away from this 30-degree angle, but that would put it in our prop wash. Now I could bring it higher, but I really don't want to do that because then I'm going to have to increase the angle of this boom. So this really is pretty much where I'm going to have this length or the position of the inverted V-tail. So instead of doing a direct calculation of where this length is, I ended up using some restrictions from these angles and the restriction of trying to keep out of the prop wash, and that pretty much placed where this tail is going to be. Now if I did not have the restriction of trying to keep out of this prop wash, I probably would not have used an inverted tail to start with. Then what I probably would have done is bring these booms down so they're almost straight back, so they're just barely above this 12-degree line. I would have put the horizontal surface connecting the two booms together, and then I probably would have put twin rudders or twin vertical surfaces on the booms, one on each boom. That's probably would have been what I would have done if I decided to go with a more conventional tail instead of this inverted V-tail. Now, as you probably know, on a lot of pusher configurations, this prop is higher and there's a single boom that comes out the bottom of the wing and comes back to a fairly conventional tail. And then also we could have actually lowered this wing then because we don't have to deal with the prop clearance. Then all we have to deal with is making sure that our flaps clear the ground when we're landing. And of course, if you don't have any flaps, you can come even lower down. So using the measure mechanism in OpenVSP, I did a measurement from the 25% chord of the main wing to the 25% chord of that tail that we came up with, and it is 13.6 feet for that length. So now we know the length of our tail, we can come up with the surface area for our tail. So now we come back to this equation here. So we've already looked at these numbers that we plugged in. So now we need to plug in our length number. We can come up with the surface area for a horizontal tail. Now keep in mind, Raymer says that for a V-tail, the way you come up with the surface area for that is you calculate a horizontal surface area, a vertical surface area, you add those two together, and that's a surface area for your total V-tail. So that's what we're going to do. We plug in our 13.6 here, and we come up with a horizontal surface area of roughly 8 feet. For the vertical tail, we do the same thing, and we come up with a surface area of 6.23 feet. So we add the horizontal area, the vertical area together, and we get 27 square feet for our entire vertical tail inverted V configuration surface area. Now, in order to get the span and chord, I used OpenVSP to do that. So I already talked about how I came up with the shape of the tail, how high it is, how wide it is here at the top, and this little vertical area here. So looking at the front, so I used all my restrictions to come up with this shape here. So that ends up being the span of our vertical tail. So then in order to find out what that span is, I come up here to this plan section for the vertical tail, and it tells me that I have a 10-foot span from this spot up over the top and back down to this spot. Now that's not projected span. That's not the span that you see from here to here. It's the entire thing. Now projected span is around 7.8 feet, and that's about right. Because I want to be able to remove the outer wing panels and then slide the center section, the boom, the tail, all put together, slide that into a trailer. We've got the span, we know what our surface area is, so we divide span by surface area, and that gives us our chord. But OpenVSP does that for us. So we can look here and see our chord is 2.7 feet. So this is pretty much all the information that we need at this point in our design to know what size and geometry our inverted V-tail is going to be. So the next video will proceed on to what the next thing is in Dan's book. And the next thing is talk about the size of the fuselage, and that's on page 39 of his book. So that will be our next video. And before we close out this video, I wanted to give a fantastic thanks to all the patrons that are supporting the channel. And I want to give a special thanks to those guys who have joined the Discord server. I wanted my patrons to get on there early, help me test it out, and that's been going fantastic. Keith and Shane and the other guys have been doing a good job of testing it out, adding content, sharing the findings that they've been coming up with on their own designs, and it's been a lot of fun. Now, if you'd like to see the activity that's going on the Discord server, I'll put a link down in the description of this video that you can click on, that you can go and see what's going on. Now, if you'd like to join the Discord server where you can interact and leave your own comments, then the best way to do that is to become a patron on Patreon. And once you let me know you're on the Discord server and what your username is, I can give you permissions to start adding comments. Now, you may notice that there's a few channels on the server that's called Keith's Project and Shane's Project. Keith and Shane are both designer tier patrons on Patreon. And being a designer tier, they get their own channels on the server where they can share some of the design details of the projects that they're building and designing. And any builder tiers that we get will also get that same privilege. So I invite you to click that link down in the description and check it out. Well guys, until next time.